In this slide, we explore the connection between Newton's second law of motion and momentum. The law provides a fundamental way to understand how forces affect the motion of an object through the concept of momentum. If Pi equal to mvi represents the initial momentum and Pf equal to mvf represents the final momentum of the system, then the change in momentum can be expressed as Pf minus Pi equal to mvf minus mvi. Here, m is the mass, vi is the initial velocity, and vf is the final velocity of the system. If this change in momentum occurs over a time interval t, we can calculate the rate of change of momentum. Rate of change of momentum is equal to mvf minus mvi, the numerator divided by the time interval t. We observe that the numerator represents the momentum change, while the denominator represents the time interval over which this change occurs. Recall that acceleration is defined as the change in velocity over time. A is equal to Vf minus Vi divided by the time. Substituting this into our equation for the rate of change of momentum gives mVf minus mVi divided by t is equal to ma. Thus, we can conclude that the rate of change of momentum is equal to the product of mass and acceleration. From Newton's second law, we know that the resultant force acting on the system is equal to the mass of the system multiplied by its acceleration. Thus, resultant force is equal to ma. Combining these equations, we establish the relationship. Rate of change of momentum of a system is equal to the resultant force acting on the system. Let's take a closer look at example 4. In this scenario, we have an object with a mass of 20 kg that is initially traveling north at a speed of 10 meters per second. A resultant force acts on it for a duration of 2 seconds, causing the object to slow down to 6 meters per second. Our task is to calculate the magnitude of the resultant force applied to the object. To solve this problem, we apply the formula derived from Newton's second law. Resultant force is equal to mVf minus Vi divided by the time. Here, m is the mass of the object, Vf is the final velocity, Vi is the initial velocity, and t is the time interval during which the force acts. Let's substitute the given values into the formula. M equal to 20 kg, Vf equal to 6 meters per second, Vi equal to 10 meters per second, t equal to 2 seconds. And plugging this into the equation, we obtain the resultant force to be equal to minus 40 Newton. The negative sign indicates that the force acts in the direction opposite to the object's initial motion, which makes sense because the object is slowing down. However, since we are asked for the magnitude of the force, we take the absolute value of 40 newtons. Here, we will summarize the key concepts of Newton's second law of motion and its relationship to momentum. We have learned Newton's second law, which established the relationship between force, mass, and acceleration. We walked through examples that apply Newton's second law to real-world scenarios. These include step-by-step problem solving. Consider a person in the elevator. When the elevator is accelerating upward, the person feels heavier due to an increased normal force. When the elevator is decelerating downward, the person feels lighter as the normal force decreases. Linear momentum is defined as P equal to mv, and we must learn how to apply the principle of conservation of momentum. We established the relationship where the resultant force acting on an object is equal to its rate of change of momentum.